Hello everyone, I'm Ray from Purdue University. Today I'm going to talk about how to mitigate the embodied carbon emission in the air-entrained concrete, because I think the embodied carbon emission is the topic of our session, right? So first I'm going to talk about the air-entrained concrete, why we need to use the air-entrained concrete, because the freeze-thaw damage is a global issue for the infrastructures. And in the United States, we have over 60% within the severe weathering regions, according to the STMC 33. So in these areas, if you design for example, the pavement bridge deck, you need to entrain the air to resist the freeze-thaw damage, right? So going to the air-entraining agent, how we entrain the air to the concrete. Normally, we use the air-entraining agent. For the air-entraining agent, we know we have the hydrophobic head and hydrophobic tail and hydrophilic head. So this amphiphilic surfactant molecule can entrain billions of air bubbles in the concrete. So that is very good. That can resist the freeze-thaw damage of the concrete, right? Everyone knows that. However, a big issue is the effectiveness of the AEA is very unstable. There are so many factors can affect the effectiveness of the AEA. So normally, if we design a concrete mixture design in the lab, we have very nice air void distribution. We have very nice air content, right? We have very good freeze-thaw damage, freeze-thaw resistant. Then if we move to the field, everything change, temperature change, material change, aggregate change. Then we find, okay, the air may not meet the requirement, air void is not stable. And go to the source of the carbon, we find, okay, everyone knows for 1% of the entrained air in the concrete may reduce about 5% of the compressive strength, right? Normally, for example, in Indiana, we need about 6.5% of the air, right? So we will reduce a lot of the compressive strength. Then if you ask a concrete engineer, how can we maintain a good compressive strength for the air-entrained concrete, everyone will tell you, okay, I will just add more cement. Why? Cement is cheap, right? And it's very effective in maintaining the compressive strength. So overdose of the cement will increase a lot of the embodied carbon, right? Another issue is a potential long-term durability issues for the air-entrained concrete with AEA, traditional AEA, because we introduce a lot of the air bubbles that is empty. That's the channel for example, chloride, oxygen, moisture to enter the concrete, right? That may cause some long-term durability issue. But when we are considering about the carbon emission of the air-entrained concrete, normally we ignore this part of the carbon source. Another thing is a rejection in the field due to the specification non-compliance. For example, last year I was in a field project. In Texas, we had like 15 trucks of the concrete in the field, and we need to do the air content measurement, right? However, the air for that 15 trucks of concrete does not meet the requirement, and we tested a couple of times. Then finally, we decided to reject that 15 trucks of concrete. So that's a lot of waste. That's a lot of embodied carbon, right? And then, according to this report, the National Ready-Mix Concrete Association, we found out, for example, 10% increase in cementitious material content for the air-entrained concrete, right, to compensate for strength loss, will result in about 9% of the increase in the carbon footprint of this air-entrained concrete. So can we try to maintain the strength while maintain a good freeze-thaw resistance without using more cement, without increase the carbon footprint, right? So in this work, we used the polymeric microspheres. This is a hollow microsphere. It's a layer of the polymeric shell encapsulating the air. So the name for this product is called expansive. So I name it as the EC in this study. So it's super lightweight. You can see in this picture, the density is lower than the water. And here is a particle size distribution. The particle size is similar to the cement particle. And for this product, there are many types of the microspheres. For this type of microspheres, it's wet, so it has some surface absorbed moisture on the surface. So we did the low temperature evaporation test to look at the moisture content. So we can find the moisture content for this product is about 95.6%. So it's really lightweight, right? So most of the weight comes from moisture on the surface. So after mixing with the cement, we did a TGA to look at the hydration degree. We find the hydration degree of the expansive mixed concrete is higher than the reference concrete without any chemical addition, and it's also higher than the AEA mixed concrete. Why? Because the surface absorbed moisture on the expansive provides a local moisture for the hydration, so it can improve the hydration degree. So it is similar to the internal curing concrete, right? And then it's the air content, because this is the biggest issue for the air-entrained concrete for the freezing resistance, right? Firstly, we use the ASTM C231 air meter. This is a compression air meter. However, we find out with this air meter, we did not observe any increase of air content for the expansive mixed concrete. Then we tried another method, ASTM C173, the volumetric method. Then we find out, okay, now the air increased a lot. Then we realize for this ASTM C233 method, maybe the pressure is not high enough to compress the expansive particle to reach the air content, right? And then you can see in here for the endowed concrete, endowed pavement, the target air content is 6.5%, and it allows for a range from 5.7 to 8.9. So we can see for these three dosage of the expansive is by the mass weight of the cement, it all follows it is all accepted by the endowed. And then it's a compression strength, because for the biggest issue for the AEA concrete, traditional AEA concrete, is the compressive strength reduction, right? So we can see very obviously with the addition of the AEA 1.5, the air content is 6.5, which is the target air content for the endowed pavement, right? So we can see the compressive strength reduced a lot compared to the reference concrete without the air-entraining, right? And another thing very interesting is, according to ASTM C57, the strength for the concrete to expose to the freezing attack is 4,000 psi. And for the reference concrete, we can see it reached this compressive strength at around 7 days. However, for the AEA concrete, AEA 1.5, it needs about 90 days to reach this compressive strength. And with higher AEA dosage, the strength is lower. So here comes a problem for those like concrete company. For example, for Indiana, in Indiana, they get the payment after the concrete reaches the target strength, for example, 4,000 psi, right? So if you use AEA, you need to wait, for example, 90 days to receive your payment. However, if you use like expansive concrete, you just need to wait like 7 days. So if you use AEA concrete, I talked with those ready-mix concrete company. They told me, okay, if in this case, AEA 1.5, if the strength is too low, I will just add more cement. Why? I don't want to wait for like 3 months to receive my money. So that's why when I'm presenting this result to the industry, they are very excited, because you can see it can maintain a pretty high, the strength of the expansive mixed concrete is actually a little bit higher than the reference concrete. Why? Because it provides a local moisture. It has a higher hydration degree, right? So that's why it has a pretty good compressive strength. Then after the compressive strength, the most big issue is, can the expansive mixed concrete can maintain a pretty good freeze-thaw resistance? So we did the ASTM C666 the freeze-thaw test, and here is the result. The dynamic modulus, we can see the reference concrete after about 100 cycles, the dynamic modulus reduced a lot. That means it has a lot of damage, right? And for the AEA concrete, very good maintain in the dynamic modulus. However, the absolute value for the dynamic modulus is low. That's why the strength is low. And for the expansive mixed concrete, at first, the dynamic modulus is higher than the AEA concrete, and is comparable, is actually a little bit higher than the reference. And then, after about 300 cycles, it still maintained a pretty good dynamic modulus. And according to ASTM C66, we need to terminate the freeze-thaw test after 300 cycles, or when the relative dynamic modulus is below 60%. So we can see for the reference concrete, after about 200 cycles, it's rejected by the specification, right? However, for the expansive concrete and AEA concrete, it still maintained a pretty good dynamic modulus. For expansive 1.5, very low dosage, the measured air content is about 5.5%, so the air is too low. Still, after 300 cycles, although it showed a pretty much reduction of the relative modulus, however, it's still higher than 60%. And the relative mass, this is an indication of the surface scaling, right? If the concrete lost a lot of mass, that means a lot of surface damage. So we can see for the reference concrete, it lost a lot of mass. And for the AEA concrete, it also lost a lot, although it maintained a pretty good modulus. But there's a lot of damage on the surface. Why? Because the strength is too low, a lot of empty air bubbles in the concrete, right? And for the expansion concrete, it showed a pretty good surface mass, the mass maintained. And here is a picture of the concrete beams during the fringe thaw resistance test. So this is the initial concrete beam. We can see clearly the finishing surface. And after 100 cycles, we can see for the reference concrete, we can see a lot of surface damage in here. That's why it lost a lot of mass, right? And for the AEA concrete, pretty good after 100 cycles. And for the expansive concrete, also pretty good surface after 100 cycles. However, things have changed after 200 cycles. We can see for the reference concrete, a lot of coarse aggregate exposed out, a lot of surface damage, right? And for the AEA concrete, although the relative modulus is pretty good, that means, okay, it maintained a pretty good strength. However, it cannot resist that much of the surface damage. So we can see for the AEA concrete, it exposed a lot of coarse aggregate, especially for AEA 2.5, more air content, lower strength, more damage on the surface compared to the AEA 1.5, right? And for the expansive concrete, we can still find the initial casting surface after 200 cycles, a little bit of damage on the surface. And then after 300 cycles, for the reference concrete, it gets worse. We can see a lot of damage, and it's the same for the AEA concrete, a lot of damage on the surface. And for the expansive concrete, still we can find the initial casting surface, a pretty good resistance on the surface damage during the fringe thaw cycles, right? After that, we did some microstructure characterization. So first is SEM observation. So we can see for the reference concrete without the entrenched air, we can see a lot of damage, a lot of cracks, right, around the aggregate, and the damage penetrate into the paste. And for the AEA concrete, we can see a lot of entrenched air bubbles. That's why it can maintain a pretty good fringe thaw damage. And for the expansive concrete, we can see a lot of very fine distributed expansive voids in the concrete, so that's why it can maintain fringe thaw resistance. After that, we also use the micro-CT to look at the in situ air void structures. We also use some other test methods, for example, the MIP, mercury intrusion porosimetry. We also use the optical microscope, such as the rect air, to look at the pore structure. However, for those traditional methods, those are, for example, rect air, that's a two-dimensional characterization. For the micro-CP, it's also a pressure method. We cannot characterize the real void structure of those expansive mixed concrete. So we decided to use the micro-CT, and then we scan the sample, we core drill, we scan, we have different layers, so we have 2D image, and then we have a series of the image. So this image shows the reference concrete after the fringe thaw. You can see these are damage, a lot of damage, right? Before the fringe thaw, we can see a lot of entrapped air in here. After damage, we have a lot of cracks. And then we have three-dimensional reconstruction of the air void system, so we can look at the air void system, the real air void system. And then here is the result, air void content before and after 200 cycles of the fringe thaw. So we can see for the reference concrete without entrained air, a lot of increase of the air content. This is not the real air content. This is damage increase. This increase is a damage, right? And for the AEA concrete, we can see still the increase of the air content. This is the damage inside the concrete. And for AEA 2.5, with more air, less damage, but still we have the damage. And for the expansive concrete, we can see after the fringe thaw cycle, 200 cycles, just a little bit increase of the air content. And another thing for the fringe thaw resistance of the concrete is not only the air content is important, but the air void distribution is also very important. That is the concept of the here. So we can see the number of the void after the fringe thaw for the reference concrete increase about 10 times. That's a lot of damage, right? And for the AEA concrete, we can also observe a lot of increase of the void number that is caused by the the freeze-thaw damage. And for expansive concrete, we can see before the freeze-thaw exposure, we can see a lot of the void number is way higher, way more than the reference and AEA concrete. And after 200 cycles, it reduced a little bit. Why? Because it has continuous hydration. It can seal some very fine capillary pores, right? And then here is the distribution of the air void before and after the freeze-thaw exposure. We can see for the reference concrete, after the 200 cycles of the freeze-thaw, a lot of increase of the void number that is caused by the freeze-thaw damage. So it generates a lot of micro cracks in the concrete. And for the AEA concrete, we can see also after 200 cycles of the freeze-thaw, a lot of increase of the air void number, especially in this small air void number that is micro cracks. And for the expansive concrete, after 200 cycles, it reduced a little bit because of the continuous hydration, right? The local moisture provides for the water to continuous hydration. And then the conclusion first is for the air-entrained concrete with similar freeze-thaw resistance, achieving the same target strength using microspheres can reduce the amount of cement required, because in this study we found out if you use the microspheres, it can increase a little bit of the compressive strength. So if your target strength is just 4,000 psi, you can actually reduce some cement. But for AEA concrete, you need to increase about 10% of the cement. Another thing is the compression method does not accurately reflect the entrained air from the expansive. However, the volumetric method is a good method to measure the entrained air by the expansive. With 2.5 and 3.5 of the expansive addition after 300 cycles, the relative modulus comparable to the concrete with 6.5 and 10% of the entrained air. After 300 cycles, the expansive concrete maintained a higher dynamic modulus value and experienced less mass loss than the traditional AEA concrete. And the expansive entrained air concrete demonstrated a more uniform air void distribution compared to the traditional AEA concrete. All right, thanks.